Question 30. Question 30 says, will the following decay take place? If no, what conservation law does it violate? So it gives us an omega minus decays into a lambda 0, a non-charged lambda, plus pion minus. Okay? So a lot of these particles that we are talking about, baryons, mesons, they are very unstable and they decay immediately into other particles. And we have discovered the decay mode a lot of the particles. So if you are given a certain decay mode, you have to determine whether it is allowed by certain conservation laws. We know that the charge has to be conserved. The charge on the left must equal the total net charge on the right. Baryon number on the left must be equal to the baryon number on the right. You can't just create all of a sudden a new baryon, or you can't destroy the baryons, right? Strangeness, the property known as strangeness, must also be conserved on both sides. So are all three conserved? If all three are conserved, then it will take place. If the reaction, the decay will take place. If both A and B are not conserved, then you put D, okay? So let's look at it. Is charge conserved? Well, you can see here, -1, 0, -1. It is already given to you. So you can see that the charge is conserved. Now, let's say it was not given to you, the lambda minus. Okay? So if it was written like this, well, charge was not given to you, then you would have to look up at the table. You would have to see, when you look at the table, you actually see that there's only one omega. Okay? The antiparticle of the omega has a plus charge. The particle itself has a minus charge, right? And the quark makeup of the omega is strange, strange, strange. Okay? So from there you can determine what its charge is. What is the charge of the strange quark? Well, if you look at the table, the strange quark has a charge of -1/3, -1/3, -1/3, -1/3. So you have no other choice. The charge of the omega is -1, right? Then you look at the quark makeup of the lambda, right? And you actually see that the lambda also only has one option. The lambda is uncharged. And the quark makeup of the lambda is up-down strange. Up-down strange. What's the charge of the up? That's +2/3. What's the charge of the down? -1/3. The charge of the strange quark, -1/3. 2/3 -1/3 -1/3. That gives you a charge of 0. So you don't have any other options unless you go to their antiparticle. If this was their antiparticle, the symbol would be, they would put a bar over it. So since the bar does not exist, we know that we're talking about the particle itself. Okay? Now, the pi actually does have two choices. You can be a positive pion, and you can be an uncharged pion, right? So there's two choices here. Well, in order for you to know which one they're putting there, the problem would have to tell you positive, or it would have to tell you 0, the uncharged pion. You have two choices, right? If they had put the 0, then we would have known this is a -1, 0, 0, then charge would not be conserved. And therefore we would say the decay is not allowed. Charge is not conserved. Okay? So the problem has to at least give you the charge of the pion, right? So let's say it did not give you this, it did not give you this. In this case, it had given it to you, and it had told you that it's the pion positive. Okay? So here is the quark makeup of the pion positive. The pion positive is made up of up quark and an anti-down quark. Pion positive, up, and anti-down. Okay, so from there, what is its charge? 2/3. The anti-down has a charge of +1/3. What's the charge? +1. Okay, so now that it had given you this pi plus, you can say charge is conserved. Okay, what's the baryon number? Okay, well, is this a baryon? The omega? It is a baryon, right? Baryon number 1/3, 1/3, 1/3. The baryon number of all the quarks is 1/3. The baryon number of the anti-quarks is negative 1/3, right? So 1/3, 1/3, 1/3, positive 1. So if it's a baryon, its baryon number is positive 1. If it's an anti-baryon, then it would be negative 1, right? So in this case, the baryon number of this one, positive 1. Is this one baryon? Yes, 1/3, 1/3, 1/3. The baryon number, positive 1. Is this a baryon? No, that is a meson, right? Baryon number of this one, 1/3. Baryon number of anti-quark is negative 1/3. What's the baryon number? 0. Why? It's not a baryon, right? So this is baryon number 0. So far, is it allowed? 1 equals 1? Yes, baryon number is conserved. How about strangeness? Is a strangeness conserved? Okay? So, what is the strangeness property? Okay, remember when in an earlier problem when I had given you the quarks, I had told you that they have a strangeness property. Only the strange quark has a strangeness property of negative 1. The strange quark, strangeness property of negative 1. All the other quarks have a strangeness property of 0. Okay? So this one, the strangeness property negative 1, negative 1, negative 1. Okay? What's the strangeness property? Negative 3. Right? What's the strangeness property of this? 0. Okay? What was the quark makeup of the lambda? I just erased it over here. The lambda was the down strange, up, down strange. Okay, what are the strangeness properties? 0, 0. It has one strange quark, therefore strangeness property negative 1. Here, strangeness property negative 3. Here, strangeness property negative 1. The strangeness property is not conserved. Negative 3, negative 1, this is 0. Okay? So, the strangeness property is not conserved. Therefore, this decay will not take place. So, which will the following decay take place? If no, what conservation law does it violate? C, strangeness. Now let me show you what the actual decay mode of the omega is. The actual decay mode, one possible decay mode is this. So it's omega goes into the chi, it's written like this, plus pi minus. So this is an accepted decay form of the omega minus. Let's write down the quark makeup, SSS. The chi, we talked about that before. It's a baryon, and its quark makeup is up, strange, strange. Up, strange, strange. So that would be 2/3 minus 1/3 minus 1/3 charge. So it's a neutral charge. And then the pion minus would be the antiparticle of the pion plus. Okay, antiparticle of the pion plus. So pi minus would be anti-up and also a down quark. Okay, anti-up and down quark. This would be a charge of minus 2/3. This is a charge of minus 1/3. So this is a charge of minus 1. Okay, so in terms of charge, you are conserving charge. Okay, in terms of baryon number, this is a baryon, this is a baryon, this is not a baryon, so you are conserving baryon number. Okay, how about strangeness? Negative 1, negative 1, negative 1, negative 1, negative 3, and this is strangeness, negative 1, negative 1, negative 2. No strangeness. Now, you're going to argue, well, even this decay is not conserving strangeness property. It seems to be reducing by minus 1, right? Instead of minus 3, it's minus 2. In the earlier decay mode, it was minus 3, and this was minus 1. It was being reduced by minus 2, right? We said that that one is not allowed because strangeness property is not being conserved. Well, it's not conserved here either. Well, as it turns out, when you study this topic, it turns out that strangeness property is only conserved in the electromagnetic interaction and the strong nuclear interaction. Only conserved via the strong nuclear interaction and the electromagnetic interaction. Decays that are mediated with the weak interaction do not have to conserve strangeness property, and as it turns out, often interactions mediated with the weak interaction, the strangeness property is reduced by 1. Okay, so instead of -3, it goes to -2. If it was -2, it might have been reduced to -1. Okay, so that means this decay mode of the omega is mediated by the weak nuclear force, and therefore strangeness property is reduced by 1. Okay, so this one is allowed because of that. Okay, so you can study up on this topic a little bit more. It gets a lot more complex and difficult, but at least this gives you a little bit of a concept of what these properties are and how to determine if a decay is allowed or not. Okay, thank you.